Okay guys, here starts the material for test 3. Alright, we're looking at chapter 8 and we're looking at dynamics in 2 dimensions. So that we have acceleration along 2 axes. Okay? So up until this point, we've really been looking at motion along a single axis or motion in a plane where we only had acceleration along an axis, so we could have motion in 2 directions but acceleration in only 1 direction. Now we're going to look at the situation where we have acceleration in 2 dimensions. So the sum of the forces in the y direction is going to equal mass times acceleration in the y direction. Sum of forces in the x direction equals mass times acceleration in the x direction. So A is going to be the square root of ax squared plus ay squared, and the directionality of the acceleration we get by theta equals the inverse tangent of ay over ax. Okay? You can apply then all of the motion equations that we had in chapter 4 to figure out the velocity in the x and velocity in y, and to help us figure out the x position, the y position, and so on and so forth. So let's start by looking just at a problem that's going to look fairly familiar to us. Okay? We're going to look at problem 1 at the end of the chapter on page 198. Okay? So let's look at problem 1 here. Now let me see if I can't blow this up a little bit. I want to make sure you can read it. It says, as a science fair project, you want to launch an 800-gram model rocket straight up and hit a horizontally moving target as it passes 30 meters above the launch point. The rocket engine provides a constant thrust of 15 newtons. The target is approaching at a speed of 15 meters per second. At what horizontal distance between the target and the rocket should you launch your rocket? Okay, now, at first glance, you're going, what do you mean? Well, this is a situation where we're trying to make things meet. So we've got an x motion and a y motion, and we want them to end up at the same location in space at a given moment in time. So let's draw a picture. Okay, now this one's a really simple one. So we have a rocket here, whee, okay, and it wants to go up so that y final is 30 meters, okay, y initial 0 meters. Now, call this x final, and over here some x initial, okay? And I've got a target that's moving like this. This is its x final, this is its x initial. Now for the target, v is constant, and it's 15 meters per second. Now, let's think about the rocket. The rocket, okay, has the thrust force acting on it and force due to gravity. The mass of the rocket is 800 grams, that's 0.800 kilograms. So force due to gravity on the rocket has a magnitude 0.8 times 9.8 of 7.84 newtons. Okay? So the sum of the forces in the y direction equals mass times acceleration in the y direction. So I have T plus force due to gravity equals mass times acceleration in the y direction. So T was given to us as 15 newtons. The force due to gravity is minus 7.84 newtons. The mass is 0.800 kilograms times acceleration in the y direction. So 15 minus 7.84 divided by 0.8 says the acceleration in the y direction is 8.95 meters per second squared, and it's positive. I'm going to caulk this a little bit so we have more board that we can see. So now, I want to figure out how much time it's going to take me to get to y max. So for the rocket, I can say that y final equals y initial plus v initial y delta t plus 1/2 ay delta t squared. Now I know y final is 30 meters. Y initial is 0. It starts from rest, so velocity initial is 0. Delta t plus 1/2 times 8.95 meters per second squared delta t squared. So 30 divided by, 30 times 2 divided by 8.95. Delta t squared then is 6.70. Take the square root of that. Delta t is 2.59 seconds. Okay, now I can look at the target. I know that x initial we're going to call 0. X final is what I want to know. So I can say that x final equals x initial plus v initial x delta t. So x final is going to be 0 plus 15 meters per second times 2.59 seconds. It says that x final is 38.8 meters. So your target needs to start moving at x initial, which is 38.8 meters, the way I've drawn it, to the left of the rocket at time 0. So you'd want to have a button that you hit that released this guy at the same time that your rocket took off. Now, I would probably, in a real life situation, you'd have to start it out back here, get it up to 15 meters per second so that they would meet, but that's not what the problem asks us to do. Okay? So that's a really simple 2D motion problem where I have two objects that I want to have meet at a location in space. Looks very reminiscent of problems we've already done. Now, let's move on. The type of 2D motion that we're going to be most interested in this chapter is circular motion. Okay, motion along that circular pathway. And we know we have two situations. Motion around a circular pathway where we have a constant speed, and motion along the circular pathway where we have a changing speed. Okay? We know from earlier work that an object moving around a circular pathway at a constant speed is called uniform circular motion, and that it has a centripetal acceleration, which means it has to have a centripetal force that causes the object to turn. With this in mind, let's kind of review circular motion. Okay? get it reset in our brain, and talk about then the force. So for uniform circular motion, the tangential velocity is constant, and the angular velocity, omega, is equal to v sub t divided by r. Okay? The centripetal acceleration is equal to v squared over r, or omega squared times r. Now when we're calculating like this, okay, remember that what we're getting is the magnitude of the acceleration. Now the one thing we want to remember about centripetal acceleration is that it's center seeking. That means that it's always pointing in toward the center of the circular pathway. So we can say sum of the forces centripetally has to equal mass times acceleration centripetally. All right? So let's look at circular motion and the forces behind circular motion. Now, we're going to introduce a new coordinate system here. We kind of hinted at it when we were looking at circular motion before, but here we go. This one is a new one. To explore circular motion, we can't use the regular XY coordinate system with the origin based at the center of the circle. We get a mess. When we're exploring circular motion, we're going to use the RTZ coordinate system. Okay? Now, the r-axis is along a radial line that points in toward the center of the circle. The t-axis is always tangent to the circular pathway, and the z-axis is perpendicular to the plane of r and t. Now, things to remember here. The plus r-axis points in toward the center of the circle. We're not kind of used to that, but the plus r-axis points in toward the center of the circle. The plus t-axis points in the counterclockwise direction, and the plus z-axis is up from that plane. So here's the RTZ. The other thing to notice about the RTZ coordinate system is that it's based on the object. So this origin of this coordinate system moves. Okay, so it's not something we're used to. But this is the first time you see it. So the RTZ coordinate system. Now, if we have an object that's undergoing non-uniform circular motion, okay, then we can have an acceleration in the r direction. Well, they just took an a vector. If I have an a vector here in the RTZ coordinate system, then based on angle phi, it's got an AR component and an AT component. We'll see that come into play when we have a non-uniform circular motion happening, where we're going to have a centripetal acceleration and a tangential acceleration. So, for uniform circular motion, V sub r equals 0. V sub z equals 0. So there's no velocity in the radial direction. There's no velocity in the tangential direction. The z direction. The tangential velocity is equal to omega squared r, which is equal to 2 pi r over t, where t is the period, and that's going to equal a constant. The acceleration tangentially is 0. Acceleration radially is 0. In the z direction is 0. A sub r is omega squared times r, v squared over r. One thing I want you to notice here is that the radial acceleration depends on the tangential speed or the angular speed. So if you change tangential speed, you change angular speed, you have to change the radial acceleration. Okay, so this means the sum of the forces radially equals ma sub r. Sum of the forces in the z direction is equal to 0. Sum of the forces tangentially is equal to 0. So note that the velocity vector points along the t-axis and the acceleration vector points along the r-axis. So since they are perpendicular to each other, okay, the radial acceleration is just a turning acceleration. It causes the object to change direction of travel, but does not change its velocity. Does not change the speed. So, if we apply Newton's laws to circular motion, we can say the sum of the forces radially equals mass times acceleration radially, which equals m v sub t squared over r, or m omega squared times r. Sum of the forces tangentially equals 0, and the sum of the forces in the z direction equals 0. All right. I have not worked out the problem set to give you for this yet. Let me see. So I'm going to stop right here, and then I'm going to work the problems, and then we'll go over them. Okay, guys, here we go. We're going to start problem solving, and we're going to start with problem 5 at the end of the chapter. Okay? So, if we look at problem 5 at the end of the chapter, let me read it to you. It says a 1,500 kilogram car drives around a flat 200 meter diameter circular track at 25 meters per second. What is the magnitude and direction of the net force on the car? All right, now let's slide over so that we've got plenty of whiteboard space. Okay, I'm using a different room today, so I'm judging my whiteboard space. Let's see. How am I doing there? I can go out a little bit further. How's that? We're good. If I scoot it over this way, I can still go a little bit further. All right, so I know where I need to stay in. So if we look at problem 5, the first thing that it asks us is, says, what is the magnitude and direction of the net force on the car, and what causes the force? So on 5, we're asked force net, okay? That's going to be in newtons, and we're asked cause. Now, the pieces of information we're given is the mass is 1,500 kilograms, and that the diameter is 200 meters. That means the radius is half that, 100 meters, and that the car has a tangential velocity of 25 meters per second. Okay? That's all the information we're given. Now, when this sucker is going around a circular pathway, we know that the sum of the forces radially has to equal mass times the acceleration radially. Okay? Now, let's find the sum of the forces radially. That would have to equal the mass, which is 1,500 kilograms, and times a sub r. Now, we can get a sub r because a sub r is going to equal v sub t squared over r. So I'm going to substitute that in. Sum of the forces radially equals 1,500 kilograms times v sub t squared over r, which means I have 1,500 kilograms times 25.0 meters per second over 100 meters, and that's 25.0 meters per second squared over 100 meters. So if we solve this, what we get is the sum of the forces radially is equal to 9.38 times 10 to the 3 newtons. Okay, so that's the magnitude of the force that it takes to turn the car. And the cause is static friction. I know that doesn't sound reasonable if the car is moving, but in the R direction, you've got static friction that is keeping the car going around the circular pathway. In the tangential direction, a rolling tire is going to have rolling friction. So on your tires, while it's going around the curve, there are two kinds of frictional forces. There is the static frictional force along the radial axis and a rolling frictional force along the tangential axis. Okay? So let's move on and look at problem number 8. Now guys, it'd be a good idea if you had your textbook out so that you could be looking at these problems as I'm reading them to you. Okay? I don't know how to get the document camera to come up in this room, so I'm winging it. Problem number 8 says that the Bohr model of a hydrogen atom, an electron of mass 9.1 times 10 to the minus 31 kilograms, is in an orbit at a radius of 5.3 times 10 to the minus 11 meters. And the proton pulls on the electron with a force of 8.2 times 10 to the minus 8 newtons. It says, how many revolutions per second does the electron make? So what we're asked is to find omega in revolutions per second. Okay? Well, we know sum of the forces radially has to equal mass times acceleration radially, and acceleration radially is equal to omega squared times r, so m omega squared times r. So let's plug in the things we've got. Well, I know that my force radially is 8.2 times 10 to the minus 8 newtons. That has to equal the mass, 9.11 times 10 to the minus 31 kilograms, times omega squared, times the radius, 5.3 times 10 to the minus 11 meters. So if we solve for omega squared, okay, omega squared is going to be 1.7 times 10 to the 33 radians squared over seconds squared. So if we solve for omega, I get 5.12 times 10 to the 18 radians per second. Okay, now it wants it in revolutions per second. So 4.12 times 10 to the 18, let me make my 8 better, radians per second, times 1 revolution for every 2 pi radians. Notice the radians and radians divide out. We get 6.56 times 10 to the 15 revolutions per second. Okay. These problems aren't really hard. You just have to keep applying the equations. Now, let's look at problem 12. We're going to kick it up just a little bit here. Okay? We look at problem 12. It reads, a 5-gram coin is placed 15 centimeters from the center of a turntable. The coin has static and kinetic coefficients of friction with the turntable of static 0.80 and kinetic 0.50. The turntable very slowly speeds up to 60 RPMs. Will the coin slide? Okay? Now, essentially what they're asking us here is F sub s max enough to keep the coin turning? Okay? So one thing we want to get is F sub s max. Okay? That's one thing we want to solve for. And we want to solve for force radial, and then we're going to compare the two. Okay? Now the pieces of information we're given the mass is 5 grams, so that's 5.00 times 10 to the minus 3 kilograms. We're told that the radius is 15 centimeters, so it's 0.150 meters. And we're given mu sub s is 0.80. Now they gave us mu sub k, 0.50, but that's information we don't need. That's extra information. And then we're told the angular acceleration final, on the angular velocity final, is 60 revolutions per minute. Now I need that in radians per second. There's 2 pi radians for 1 revolution. And for every 1 minute, there's 60 seconds. So I get 6.28 radians per second. Okay? Now, if I do the sum of the forces radially, that has to equal m omega squared r. So sum of the forces radially has to be equal to 5.00 times 10 to the minus 3 kilograms times 6.28 radians per second, square all that, times 0.150 meters, and I get a force of 0.0296 newtons. That's my force radial. So that's 0.0296 newtons. Now, I need to figure out F sub s max. Okay, if you think about that coin, and let's say this is my plus r axis, okay? This is my z axis, plus z axis. Then I've got a normal force here, force due to gravity here, and our F sub s that has to be pointing in this direction. So the sum of the forces in the z-axis would be the normal force plus the force due to gravity, and that's going to be 0. So the normal force plus the force due to gravity, which is 0.049 newtons, equals 0. Oh, negative there. The normal force is 0.049 newtons. So F sub s max is going to be 0.80 times 0.0490 newtons, which is 0.0392 newtons. 0.0392 newtons. As long as F sub s max is larger than the radial force needed to keep it turning, the coin is going to stay in place. And as we can see here, the maximum frictional force is larger than the force needed to keep it turning, so the coin will keep going around in circles on the record, on the turntable. Okay, now I want us to look at page 102 and look at problem 46. Now I like 46 because this one's got a little bit more work to it. Okay, let's get ourselves some working room here. Okay, problem 46 reads, two wires are tied to a 300-gram sphere shown in figure 8.46. The sphere revolves in a horizontal circle at a constant 4.5 meters per second. What is the tension in each one of the wires? Okay, so this is number 46. All right, let's start out with the free body diagram. There's my plus Z axis. This is my plus R axis. Okay, so there's a tension in that top wire. There's a tension in the bottom wire. I call them T1 and T2. There's force due to gravity. Okay, now, force due to gravity in magnitude is going to be 0.300 kilograms times 9.80 meters per second squared. So it's 2.94 newtons. Now we were given angles, well, we were given lengths. From the lengths, I found out the lengths of this wire and the length of the pole, that this is 30 degrees and this is 30 degrees. Okay, it's worked out in the notes that you're given. I'm not going to work it out here. Okay, and we're also told that V sub t is equal to 7.2 meters per second, and that R is going to be 1 meter cosine of 30 degrees, so 0.866 meters. All right, now, if I think about my tensions, I'm going to have a T1Z and a T1R. I'm going to have a T2Z and a T2R. So I know that T1Z in magnitude is going to be T1 times the sine of 30 degrees. T1R in magnitude is going to be T1 cosine of 30 degrees. T2Z in magnitude is going to be T2 sine 30 degrees. And T2R is going to be equal to T2 cosine 30 degrees. What I wanted to figure out is I'm wanting to find the tension T1 and the tension T2. Okay? Now, things we also know. Some of the forces in the Z direction have to add up to be 0. So in the Z direction, I have T1Z plus T2Z plus force due to gravity has to add up to be 0. So I have T1 sine 30 degrees plus a minus T2 sine 30 degrees plus a minus 2.94 newtons has to be equal to 0. I can simplify this down to magnitude of T1 plus the magnitude of T2 being equal to 22, let's see, being equal to 5.88 newtons. Okay, so I'm going to box that in. Now, if we look at the sum of the forces radially, that has to equal mass times acceleration radially, which is mv sub t squared over r. So I have T1 cosine 30 degrees plus magnitude of T2 cosine 30 degrees is equal to the mass, 0.300 kilograms, times the velocity, 7.2 meters per second squared, over the radius, which was 0.866 meters. So this comes down to the equation T1 plus T2, magnitude T1 plus T2, has to equal 22.5 newtons. Okay, I have two equations and two unknowns. It's a solvable system of equations. If I were, excuse me, I left a negative sign out there. That's a negative. If I were to add these two equations together, notice that the T2 is going to add out. I'm going to end up with 2T1 equals something. Okay, so if I add these two together, let me erase a little bit here because this board is not tall enough for me to do this. Okay, so I'm going to erase. I'm going to bump this guy up. So if I just write T1 minus T2 plus T1 plus T2 equals 22.5 newtons. If I add these together, I get 2T1 is equal to 28.38 newtons. Okay, if I solve for T1, I get 14.2 newtons. And then I go back and substitute into either one of those, I get T2 is equal to 8.30 newtons. Now it makes sense that T1 is greater than T2 because T1 in the z direction not only is working against T2, but it's working against the force due to gravity. So I really like this problem and I wanted you guys to see it. Okay? Now, let's move on. Let's talk about the situation of a car going over the top of a hill. A curved surface. Since it's a curved surface, circular motion applies. The force causing the car to turn is gravity. Okay? Now, you can have a normal force from the ground pushing up on it, or you could be going so fast that just at the top of the hill, there is no normal force on you, and the only force acting on the car in the R direction is gravitational force. If you're going at a speed faster than what gravitational force can use as a turning force for you downward on your car is going to fly off the road. Whee! Which, by the way, guys, sounds lots of fun until you get the bill for the damage to your car. Okay? So let's scroll down here. And we're going to look at problem 18 at the end of the chapter about a car going over the top of a hill. Well, I tell you what, you guys look at that. It's a really simple problem. I've got it solved for you. You guys try it on your own. Let's talk about a car taking on a flat curve on a highway. So instead of going over a hill, now you're going around a curve. Okay? So let's think about the car taking on this flat curve. So if the car wants to take a flat curve at a constant speed, then let's think about the forces acting on the car. Okay? We know that it's got a velocity in the direction the tire is pointing, perpendicular to the direction the car tire is traveling is a static frictional force. So on the car, on the flat road, there's a normal force, a force due to gravity, and a static frictional force.